Hello, today we have our first video for acids and bases. So acids and bases is going to be one of our biggest units of the year. This will be covered in chapters 16 and 17 in our textbook. And a lot of the concepts that we learned last unit in equilibrium will be applied to our acid and base problems. All right, so first thing I would like to do is start with a quick review of some of our properties of acids and bases. So hopefully you remember some of this from Regents chemistry. So acids would have a pH less than 7, and bases would have a pH greater than 7. That would be two of our most important things to know, and we will talk more about the pH scale in a couple of videos. When you get an acid on you in lab, hopefully you don't, but it has more of a burning feeling, and bases tend to feel slippery when you get them on your skin. Acids have more of a dilute acids have a sour taste, whereas bases are bitter. And by no means am I saying we should be taste testing our substances in lab. Acids ionize to produce the hydrogen ion or the hydronium ion. We'll talk a little bit about that later. Bases ionize to produce the hydroxide ion in solution. Both acids and bases are conductors of electricity, and the stronger they are, the better conductors they are, and that will have to do with how much they ionize in solution. We'll be talking about that. They also both react together to form a neutralization reaction. And when we do a neutralization reaction, we form an ionic salt and water. All right, now there's lots more properties, and we will be getting at those throughout the unit. But this is a good review of some of those basic ones from Regents Chem. All right, so one of the things that we wrote on our list was that when acids ionize, they produce the hydrogen ion. That is the Arrhenius definition of an acid and base. So if we think about something like HCl, when that ionizes in solution, it splits apart into the hydrogen ion and the chloride ion. And it's that high concentration of hydrogen ions that cause it to have a low pH. Now, bases, on the other hand, they ionize to produce the hydroxide ion, the OH minus ion. So if you think about our most common base, NaOH, when that ionizes in water, we get the sodium ion and the hydroxide ion. And it's that high concentration of hydroxide ions that leads to a base having a high pH. Now, on our chart, we wrote acids have or will ionize to produce the H plus or H3O plus ion. So we need to know that these can be used interchangeably to indicate the presence of an acid. In actuality, the H3O plus ion, the hydronium ion, is the more accurate representation because the hydrogen ion cannot exist unbonded in a system. So, since all of our acid and base solutions would be aqueous, water will be present. So the hydrogen ion will combine with a water molecule to produce the hydronium ion. So we need to know that both of those will be used to signify the presence of an acid. All right, in addition to the Arrhenius definition, we also have the Bronsted-Lowry definition of acids and bases. And this one is a little bit broader of a definition, so allows a few more things to be classified as an acid or a base. An acid is a proton, which hydrogen plus would be a proton because that's all that would be present in it. So an acid is a proton donor, or it loses or donates the hydrogen ion. Bases then gain or accept the hydrogen ion. So in reagents, we had this little stupid saying that people who do acid are losers. This just helped us remember that acids lose H plus. So if we look at a reaction, we see that something's losing the hydrogen ion, then we know to classify that as an acid. All right, so that will make more sense once we take a look at these reactions here. So what we do here is you have to see what your substance is turning into. So HCl is turning into Cl minus. So obviously HCl is more similar to Cl minus, and water is more similar to the hydronium ion. In order for HCl to turn into Cl minus, it must lose, or better, donate, because it's not totally losing them, it's just transferring it, donate the hydrogen ion. Therefore, HCl is the acid, which totally makes sense because HCl is an acid. The water molecule is gaining or accepting the H plus ion, so that makes the water molecule be acting as the base in this specific example. Now, if we reverse the reaction, we see that now the hydronium would be losing an H plus. That means the hydronium ion would be acting as the acid. And if we reversed this, the chloride ion would be gaining the hydrogen ion, so the chloride ion would be acting as a base. These are called conjugate acid-base pairs. So HCl, Cl minus is a conjugate acid-base pair. HCl is the acid, Cl minus is the conjugate base. Water and hydronium would be another conjugate acid-base pair. Okay, so we're going to take a look at our second example. So NH3 would be turning into NH4. In order for NH3 to turn into NH4, it must gain or accept a hydrogen ion. So that means that NH3 is acting as the base. Water would be turning into the hydroxide ion. In order to do that, it must lose an H plus or donate an H plus. So it is acting as the acid. If we were to reverse the reaction, the hydroxide ion is turning into the water. In order to do that, it would have to gain a hydrogen ion, so it would be the base. And the ammonium ion is turning into NH3 by losing or donating an H plus. So that is acting as an acid. The two compounds that you connected, NH3 and NH4, water and OH minus, are conjugate acid-base pairs. You'll notice in one example, water was acting as a base. In the other example, water was acting as an acid. Water is what we call an amphoteric substance. It can gain or lose hydrogen ions, so therefore it can act as an acid or a base depending on what else is in the system. All right, so we already started talking about conjugate acid-base pairs. So they are the two things that you connect. So in this example, HNO2 and NO2 minus are a conjugate acid-base pair. Water and H3O plus are a conjugate acid-base pair. All right, in this example, we are determining the conjugate base of the substance given. So these substances given would be acting as the acid. So we are looking for their conjugate base. So the acids have to lose an H plus. So the conjugate base of HClO4 would be ClO4 minus. For B, if H2S is the acid, that means it must be donating a hydrogen ion. So therefore, its conjugate base would be HS minus. pH 4 plus, if we take away an H plus, that would give us pH 3. And lastly, HCO3 minus, if that's acting as the acid, that means it must donate an H plus. So we have to take away an H plus, so then we would get the carbonate ion. Now notice that since we were taking away an H plus, that would affect the overall charge. All right, in this example, we are doing opposite. So these substances given are acting as the base, and we are looking for their corresponding conjugate acid. So if the substance is acting as a base, that means it must be able to accept a hydrogen ion. So if we add in the H plus ion, we get HCN. For B, if we add the hydrogen ion to SO4 minus 2, we get HSO4 minus. If we add a hydrogen ion to water, we get the hydronium ion. And lastly, if we add the hydrogen ion to HCO3 minus, we get H2CO3. Again, notice since we are adding the hydrogen ion, it is changing the overall charge.